Okay, so I introduce myself. I'm Marek Kuś from Center of Theoretical Physics, and I will not be talking about physics. So this has nothing to do with physics. So as the title suggests, this is about art and topology, and in fact, I think for me it is a nice experience as some kind of interdisciplinary work I was involved in. This is not between artists and topologists, but between, say, psychologists or neuroscience, representatives of neuroscience, and myself. So it has nothing to do with art and topology, but it will be about art. So what was the topic of this collaboration? So actually, my friends, here are these fantastic investigators I have a privilege to work with, performed rather involved experimental investigations, and the aim was to understand people's reaction on abstract art. So this is a short description. I will go to the more, I would say, profound this discussion on this experiment in the next slide. But let's summarize this in this way: that there were organized two exhibitions of art. Okay, so at the first exhibition, there were 12 pictures of a professional artist. I will show you immediately this. And there was a second exhibition, okay, a few weeks after the first one, at which there was the 12, I would say, corresponding. You'll see what does it mean, corresponding pictures, also which could be treated as abstract art, were exhibited there, and then various experiments on people's reactions were performed. So there were, okay, maybe I have something more on the next. Okay, so let's say the first exhibition was entitled 3/4 of a Black. So these are some texts from these leaflets about this exhibition. It was in Poland, in some kind of renowned gallery. And okay, so there are typical things which you can find in the leaflets about an exhibition. And this was the pictures which were exhibited. So as you see, indeed, black is dominating here. And okay, so you can see that there are some titles which obviously are completely incomprehensible, but these are authors' inventions. Okay. Okay, although these lines of black, maybe this is okay. So the second exhibition was 3 weeks or 4 weeks later in the same gallery, and it involved 12 pictures which were generated by a so-called big gun network. So this big gun network is a special arrangement of artificial neural networks, which primary aim of which was to produce realistic pictures. So to teach this network a lot of naturalistic landscapes and so on. And the idea was that it should produce some realistic pictures. But if you disturb this so-called weights of these connections in this, I'm not a specialist in neural network, so I cannot say many details about that. So you can produce also some abstract outputs, okay? And this was from Yannick, who was important there. He knows very well how to do this. This was at the time Well, there was no GPT-3 available, but there were some predecessors of that. This is a variant which was called GPT-J, and it was used to produce the names also, the titles of the pictures, okay, randomly. So these are the pictures generated by the network. So as I told you, so our primary aim was not to judge whether the network produces nice pictures or whether they are somehow as good as the real artist production, but rather to observe how people react, or whether they react differently on this and that. Okay, and to keep it, I would say, unbiased. So there was obviously nobody knew that except experimentalists that these people who made this experiment, that this is a fake art. Okay, so in the second exhibition, it was advertised as a normal exhibition of somebody. Okay, I don't know whom, but also this advertising leaflet, for example, was generated by GPT-J. It was equally good as any other leaflet about the exhibition, as you can imagine. So, and the idea was to see whether the reactions or the physiological or psychological reactions on that are different. So this is the brief description of the experiment. So actually this was the experiment was done on groups of students of the artistic Academy of Art in Toruń, and they were asked to visit the gallery. And during this visit in the gallery, there were some experiments. Okay, so connected also with eye tracking, and mostly psychological. They had to answer some questionnaire, and the part of the experiment which I am interested here and which I want to report here is connected with the second part of the experiment. So immediately after the visit, they were invited to the laboratory when they were showed again once more all the pictures, and then the eye movement and EEG was recorded. Okay, and there were also some psychological experiments. Namely, they had to fill once more some questionnaire. I will not concentrate on that because I am not a specialist in that, and but the results are also significant as far as I understand. But I want to concentrate on this eye movement description. And obviously, at the very beginning, I think that my colleagues, my participation in the experiment was that I was on both openings of both exhibitions. So this is my participation in the experiment. Okay, but obviously, I suspect that they wanted to see whether there are some results between the reactions on the first exhibition and the second exhibition, but they were not sure that there is something. I was sure that there were no differences, though I was wrong, fortunately, because it would be a shame. Okay, so you have to confront with this artist and to say them, okay, this stupid network produced better or the same. Fortunately, it was not, although I was sure that the result will be similar. Okay, so but as I told, fortunately, they were different, and okay. And then what I want to concentrate on is also only part of this result. So this is this eye movement experiment. So there are several types of eye movement, as you can imagine, but these which are most important. Yeah.
One question. Have you tried to establish, I mean, to qualify this statement that those two exhibitions, those two sets, to which extent they're in a sense similar to our impression and to which not? Because for me, for example, the neural network produced images which contain less details.
Yes, and this is the main problem. Yes, exactly. So this will be the result which I wanted to quantify. I would say that from my point of view, fortunately, this what was produced by the network was bad art. Okay.
I would say less interesting.
Less interesting, exactly, exactly. And now we want to, yes, exactly. And we were fortunate that it was so. Otherwise, I would not go with this idea, which is contained in the but this is exactly the point. Okay. So how it is? What kind of effect it has on the eye movement? Okay. This what you observed already from the first glance of the pictures. So this there are several kinds of movement classified by neurophysiologists of these eye movements, but these which are important from our point of view are fixations and saccades. Fixations, everybody knows what does it mean. So the gaze is concentrated on the vicinity of one point. Yes.
Is there any reference frame about eye movements of those particular groups of students on some other objects?
No, I don't think that something like that was done.
So then you have no scale.
Yes. Okay. So this is, I would say, there will be a relative differences between these two. And the second kind of movement are this what are called saccades. So it means that these are the rapid changes of the focal point. Okay. So okay. So there are some others. So there are which are not so important here, the micro saccades, because if you look at something, so definitely yes, there is something which are not controlled here. Okay, so these are the results. These are the results which compare first the average of amplitude of saccades and the average fixation time. Okay, so there are visible differences between this for artists, okay, on the left hand side of this left column, and so average amplitude of saccades and longer fixation for the artist pictures. So my friends were very happy because they have some hypothesis. A hypothesis is okay that when you look at something, you are really looking for something. You are searching. Okay, so that's why when there is nothing which attracts your attention, the saccades are very with large amplitude, and the focusing time is smaller. Okay. Otherwise, if there are details which somehow attract your attention, so you focus for a longer time, and saccades are smaller. Okay, so this were the hypothesis. But as I told you, fortunately, these differences were visible. Okay, so this was a search for places that attract attention. So this was hypothesis. Okay, this is somehow this is the type of heat maps of this eye movement. So averaged over the spectators, say. Okay, so this is average time of focusing on these areas. Okay,
and averaged over all 12.
No, these are two particular pictures. One
yes,
picture
yes,
is from the exhibition. We have this for all 12. Okay, but I didn't because I wanted to. Okay, so you see that these are several focusing points. So this what actually Mleche observed, that there are more details here. There are less details, and the concentration was on the few points only. And then obviously they looked for this, so this case.
But existence of these heat maps doesn't mean that basically all viewers look
concentrated at the same. Yes.
Because that's average over the
spectators.
Yes, spectators.
Okay. That's amazing.
Yeah. Okay. So then Okay, so how to interpret this in some more quantitative manner? So what was the idea? Was to apply something which is called topological data analysis. And the core of this topological data analysis actually are two things. First is that you, which are technically called filtration, and the second is homology. Okay, so which is actually the mathematical description of some particular properties of the, say, sets of points in this case. Okay, although this is so filtering. This is very simple to explain. Okay, so let's say that you observe a bunch of points. There's 5 points which are here depicted with different resolution. Okay, so if the resolution is very high, you see simply 5 points. Okay, if the resolutions are a little worse, so you see something like that, which is somehow a closed curve. Okay, and if it is even worse, more worse. Okay, worse resolution. So you simply observe a blob here. Okay, without. Okay, so you see that there is some feature which can be said that at some point this curve is formed. Okay, is born. Okay, by with some radius. Okay, and then it vanishes with some other radius. Okay, so we call it that it is born at this point and dies at this point. Okay, for this value of this resolution parameter, filtration parameter. Okay. Okay, so the idea of this persistence analysis, analysis is that when something is persistent, so it lasts for a long time. So, for example, when this filtration parameter, in this case, resolution changes, so it means that it's something important. Okay, so the second thing is a bit of mathematics here, but very shortly, because I do not want to explain too clearly. Okay, but the original idea in this the topological data analysis was to somehow construct some structures out of this data point. Okay, so you say it is this is the general construction, whatever are these points, but think about these points as some results of measurements in some many-dimensional space. So these are the results of measurement. So it could be the n-dimensional vector in d-dimensional space. Okay, so when you have a set of points in such a d-dimensional space, such that, say, they are okay, so they are independent. The general position, one would say. So it means that all these k vectors are linearly and independent. So you construct a k simplex. This is simply a convex hull of this set. Okay. Okay, and so you can see that this is a triangle or maybe some okay, point, segment, triangle, and tetrahedron, and so on, depending on time. So there is a natural concept of a phase. So this is a subset of this, which is also treated as such a simplex. Okay, you can orient this just for technical reasons. For example, if you have a segment, okay, so you can put beginning and the end, and you say that one point is the beginning and the second one is the end. So this some orientation, arbitrary. And a simplicial complex, it is a collection of such a simplices which are glued somehow, so nicely glued. So it means that you can glue two simplices if they have a common phase. Okay, and all this stuff phases of this synthesis are also part of this complex. So, okay. And it has some natural structure of, say, module over natural or natural numbers. Doesn't mean, or maybe integer numbers, better integer numbers. So this is like a linear space, but only so a little bit poorer. Okay, and then you introduce. So all this story is somehow to quantify connections between phases and their boundaries. Okay, so this is the whole story. So to this you introduce something which is boundary operator, which simply maps phase or such a simplex into its border. Okay, so triangle into its sides. Okay, it has this property that twice the applied it vanishes. Twice applied it vanishes. Okay, so and then you have two structures. One are cycles, so these are which do not have boundaries, and the second are boundaries. Okay, so these are boundaries of some cycles. Okay, of some symbols. Okay. Okay, so both are abelian, free abelian groups or this module over Z, so you can add them, make a combination of them in a sense. And because of this idempotency, so one is the subgroup of the other. And then this quotient of these two groups is called homology group. And it is called Cage homology group. And this is also a free abelian group, so it has some generators. So if you think about this model, these are this basis of this. Okay, so it has a natural notion of dimension or the rank of the group, if you want, and this is called Betty number. So this is the rank of this, and this is something. So if you calculate the Betty numbers for all dimensions for such a simplicial complex, you have some topological characterization. Okay, so this is example which you can calculate very easily according to the prescription of the previous slide. So how to differentiate between some empty triangle and such a solid end. Okay, so this such a calculation. So let's say that the zeros Betty number is 1. And beta and this first Betty number is also 1 for this empty one, and this 1 and 0 for this solid one. So this is by purely algebraic calculations you find this difference, which are very clearly visible on this picture. Okay, and in fact it is so that this beta 0 counts the number of disconnected pieces of this whole complex, and this beta 1 counts the number of holes in this. So this is clear that this both are in one piece, but this one has a hole and this does not. Okay, so and the whole idea of this topological data analysis is that you arrange this data as points in some n-dimensional space. So these are your result of the experiments, right? Then you construct simplices of different size. There are several ways of doing that. For example, you form a simplex for the points which are within some ball. Okay, so you take subset of certain diameter. This diameter will be this filtration parameter. Then you construct this simplicial complex from the simplices. And then there are also several ways of doing that. And you calculate this homology groups of Betty numbers of this obtained simplicial complex. And because everything depends on this filtration parameters, as I told you, for example, the size of the set from which you construct a simplex, so you can apply this idea of persistence. Okay, and this which are persistent once more are supposedly most important. Okay. In our case, the situation is very simple. It's more simple than here because we have a natural way of constructing the simplices and complexes and the Svetty numbers and so on. Because you can imagine that you have a rectangular array of pixels, which represents your piece of art of generating painting, say, generated painting. So you have a rectangular array of regularly distributed pixels, and then by a simplices you take points or line segments of length 1, which ends so corners in integer with beginning and ending point in integer points or squares. Okay. And because everything is two-dimensional, so there is no need to go farther with the dimension. So this is very easy. Okay, and the complexes are also called cubical sets. Are once more, these are this simplices nicely glued. Okay, so for example, here we have a complex which consists of point and this segment and this three pieces, three squares. Okay, and they are nicely glued. It means that faces of this are always common faces of this parts. Okay. Okay, and then you calculate. You have to represent how this data of this filtration. Okay, so these are more or less always the same, but there are several ways of, I would say, presenting them. So first is something which is very popular, it's called barcodes. So this set of line segments, arbitrarily put in your picture, by the length, which is this this interval of persistence, so between the birth point and death point. Okay. And persistent diagram, which is plot of these points, and persistent landscape, which is some kind of rotated persistent diagram. I will explain it. And persistent because the number of objects, so holes, disconnected parts, as a function of the filtration parameter. And here is a very simple example how to do this. So let's say that this is your object you study. Okay, this is the simplicial complex. And what I put here as the numbers is the intensity of gray. Okay, and now I assume that I observe this by some filter. Okay, which is transparent only if this intensity is low enough. Okay, so at the very beginning you don't see anything, and with the if you have a filter which transmits this light reflected by this which is this intensity of gray 0,1, you see this, you have this which are here outlined with red lines. Okay, so these are all this light gray squares. So this whole, what I observed, consists of two parts. This is one part, this is the second part, and there are two holes. Okay, this hole and this hole. Okay, when you increase this your transparency of the filter, and you now see this also this which have the intensity of gray, say 0.3. So you see this. So one hole vanishes because you already observed this pixel. There are still two parts. Okay. Then when you increase further, everything, the bridge is also visible. So you observe on the one part. And after reaching this 0.5 transparency, you see everything which is in one piece without holes. Okay, and these are these barcodes. So these are these barcodes which correspond to the fact that between 0,1 and 0,3 you see two parts. Okay, and after that you see only one part, one connected part, and so these are this which correspond to this beta Veti number 0, and these are those which are connected with this number of holes. Okay, so observe one hole between 0 and 0.3, and the two, so two holes between 0 and 0.3, and one hole from 0.3 to 0.5. So these are these persistence bars. Okay, so this is called the barcode diagram. So now this is the other representation of the same data. So you have the points which of the coordinates, which is the birth point and death point. Okay, so this is birth and death. So you can see this is correspondent. Now there is idea that you rotate this by 45 degrees, and you obtain such a pyramid. So out of that, here is a double pyramid because there are 2 points here, okay, which have the same persistence, okay. And this is the Betty curve, so it counts the numbers. Here are two different objects which are observed, okay, and then only one, and here you have 2, 1, and 0. Okay, so these are the different ways of representing this, okay, and then now you can apply this to our pictures, okay. So these are exemplary pictures from artists and from this, so the same which I showed you before, and these are this different kind of representations. So these are these barcodes, okay, so you easily see this difference between the shape of this barcodes, okay. As like observed, there are much more interesting features here. And these are these landscapes, okay, which are also very different in this case. And these are Betty curves. You cannot say anything about them, but they're also, in a sense, different for both pictures. And the same is actually true for all these 12 pictures here and all 12 pictures here. So these structures are very similar. I will not show you. This is boring, but this is more or less the same. So this is, I would say, and this is what I was insisted that I insisted that it should be visible, and it was visible here in this particular all these representations of this data.
Well,
This time it was Mark. Okay, I think it should be more stable here, especially if there is a 3-meter long cable under my feet. Okay. So, okay, so it was for, I would say, practical numerical reasons. It was done by first transforming this all pictures in the shades of gray. Because in a sense, you characterize your if you want to be fair, okay, so to do it properly, you should somehow take into account also the color. Color, as you probably observed, was not so important here, but nevertheless, it can be repeated for all channels, so red, green, and blue channels, and you see that the results for all the channels for these pictures are more or less the same, and the same concerns this fake picture. Okay, so it does not depend whether we somehow analyze this. Okay, so these are this average landscapes. Okay, average, so it means it is average over so over all the pictures of artists and all the pictures of big guy. Okay, so you see this result clearly, and the simplest scalar measure, although it's somehow contains not much information, but which is usually used in this topological data analysis, is total area under all landscape curves. Okay. Okay. So as you can imagine, I will put numbers here. These are the order of magnitude different between these two. Okay, so it would be very nice if we can prove that it is really so that somehow this gaze is focused on the regions of the picture where something happens. Okay, and to some extent it is true. I do not claim that it is always a very good match. It usually is, especially for the pictures where there are many features. Okay, you can see it clearly here. So this is again the same picture. So this is again the same which I have already shown. So these are these heat maps, and these are white crosses. Maybe you've seen them, the red crosses. These are points at which this particular feature is born or dies. Okay, so when you change this filtration parameter, which is intensity of gray. So you see that you can see not quite nice reflection of this rich structure here in this eye movement heat maps, and also here. Maybe also here, but obviously there are also some places which are, I would say, free from any complications and nevertheless concentrated. And then it's even less profound here in these pictures. This, I would say, this frugal pictures, rather frugal in this sense of having some interesting geometrical, topological. Okay, so remarks and conclusions. So physiological reactions most probably can be easily connected to topological properties of the images. So okay, so from the very beginning, my idea was okay. So what we are concentrating on some geometric objects. Okay. Not on the whites or the large areas of nothing, okay? But this was somehow the idea to qualify this or represent this in a more, I would say, strict manner, okay? Most probably, it is completely irrelevant whether we look at pictures and of the art pictures or any other picture. The effects will be the same. But okay, our experiment was with art, okay, so that's why I concentrated on that. And as I told you, so we were lucky that these pictures which were generated by this big gun were rather poor, okay, from the point of view of artistic, I would say, value, and also from the point of view of
but one could easily generate automatically much more.
Yes.
More
This is always when I say to somebody, it's okay, so maybe we can teach better this. Sure, we can. Okay, and then probably we will obtain much better. But this was not, as I told you from the very beginning, this was not our goal to somehow improve the methods of generating or to influence it somehow. Okay, so this is. And then when we continued our I would say play rather with some other pictures, mostly also with some abstract art of real artists. Okay, so this is a strange picture, but it simply gives the dimension, the area, this area under this landscape, so which is called area and dimension 0. So somehow connected with the number of disconnected pieces, with area and dimension 1, so with something with holes, okay, in this. And this cloud here is really from this 4,500 pictures which we generated before choosing this 12, which were somehow under some criterion most similar to our artist pictures or closest from some point of view. And this colored signs are for particular art. You will see this Kandinsky, fake Kandinsky. This means that we generated Kandinsky's picture by teaching the network on the collection of Kandinsky picture and trying to produce something similar. Okay, and it's Mark Rothko, Polak, Malevich, Jarema, Richter, and once more Rothko. Two Rothkos, and I would say there is very, qualitative observation that they tend to follow this diagonal much closer than the random distribution. I don't know why it is so. This is only the simple botanical observation.
No, but this is logarithmic scale.
This is the logarithmic scale. Logarithmic scale, everything looks like the straight line, but nevertheless, this does not. This cloud of completely random. So I don't know why. Okay. So maybe you want to know why there are two Rothkos. So I have a collection of Rothko's pictures from the last year. I took on the last year retrospective in Paris.
This Jarema, do you have this?
No, this is all Rothko. So he changed his style of painting. We didn't take this one. We rather investigated these two kinds. But you can see that for the single painter, there are also different styles which can be differentiated also probably by this method. Okay, but I like this. At the beginning, he was quite I would say, inventive painter. But then somehow it's also a piece of art, but kind of.
You didn't try to sell those fake Rothkos, did you?
No, I think that these are the most expensive.
That's why I'm asking. Did you try to sell those fake?
Yes, so this I took on this exhibition. Okay, so which is a large retrospective of last year in Paris. So I understand that when it was fashionable to put pieces of art in this, I would say, business centers and corporate.
Well, he didn't
offices,
like it.
Corporate offices. So he made a.
No, he did not. He did not like it. He was offered very big money.
Yes, I know.
Which he rejected because he said that it's a financial perversion.
Yeah. Nevertheless, these were also very expensive. Okay, so I think this is the time to finish.
Okay.
I had also some other part which I'm not able to say you that obviously there were other ideas how to quantify. They usually say something about aesthetic value, which I'm very doubtful that something like aesthetic value can be measured by these numbers. But nevertheless, there were some ideas how to do it, and there was a small part of this which I skip in this moment. But to be honest, so most of them were less restrictive in distinguishing with our model this and this. But there were some which were nearly as good as our method of distinguishing between these two sets of paintings. Okay, thank you very much.
Well, thank you very much, Marek. So be careful, Kazik. Be careful with the camera. So time for questions. Mikołaj.
Okay, so you use topological invariants of this kind in order to quantify the, let's say, interest or the heat of a particular part of the image, which is something I like because these invariants are both local and non-local. But I think you could, in principle, invent something, other types of measures which have this property, some kind of correlation functions between colors, coloration lengths, and things like that. And I wonder if they are not.
Definitely yes. So most of these other methods I mentioned were kind of statistical methods. So this is exactly what you suggested. So they, for example, using several filters, Gabor filter or whatever, convoluted with such a mask of convoluted, and then investigating correlation between, you know, edges here and edges here and so on, something like that. So there are many of them, okay, in this case, and I told you, some of them worked, most of them didn't. But yes, so this is idea. So the correlation, so this is the first idea which jumped into your mind, okay? So to correlate some features at this point with the same feature at that point, okay? Color, intensity, I don't know, whatever. Yes, I agree.
Then I have a follow-up. So you mentioned that you were not investigating colors, so basically that was 2D, so the actual painting and the grayscale. But I mean, the complication probably will be huge, but you can make it 4D, so 3 colors.
So,
And actual
this
feature.
is from the point of numerics, even, it is very complicated. The second thing is that this whole idea of this topological data analysis, which I explained briefly, obviously takes into account another dimension, but in some other. Okay, so from this point of view, yes. So you have this this original idea that you have vectors in some space, so then you will have three-dimensional vector attached in this point.
At each point, yes.
And then it is complicated also from theoretical point of view and also from numerical point of view. So that's why we made some, I would say, cheating, okay? We made the same but different color channels.
Mm-hmm.
Yes, I told you, I show you this.
So basically coming back to 2D.
Yes, always 2D. And in 2D, it is relatively easy to do. If you compare this with 3D or 4D, okay?
Mm-hmm.
So you lose, in a sense, this very nice idea here that actually you have on the 2 dimensions, you have real dimensions in which you analyze this with these pixels on the rectangular grid, okay? Instead, you have some abstract space with 3-dimensional vectors. Actually, RGB is even not the good idea how to do this, because in fact, if you want to do this color, so the space of colors is really 3-dimensional, but this is not RGB, because RGB is 2-dimensional. Actually, these are only, you know, such a I would say such coordinate plates. The color space is actually 3-dimensional at least, okay? Which is hue, which is more or less what we call barwa in Polish, or color. Okay, so this is something which you can connect with the dominant frequency in this. Okay, red, orange, something like this. There is saturation, which is admixture of gray or admixture of the opposite color, and there is value, which is admixture of white and black. Okay, so these are 3 dimensions. This is this value. It is somehow connected with luminosity, but there's a theory of this because there are 2 things. There are several things. First thing is some physical characterization of this. For example, okay, you can always say that this particular ray of light consists of the frequency such and such and such. You can describe this in this way. Okay. The problem is how is the physiological reaction of this, and this more or less is connected with the physiological relation, and this is 3-dimensional.
Okay. Okay. Thank you, Professor Wiki.
I think just to comment, there is even more because you have masking. If you have more than one natural color, then
yes, you can complicate it here, but this is the simplest, I would say.
My question is, if you come to your black and white analysis, several modern telephones and photographic cameras, they recognize color, faces, birds, pets, mountains, architecture, and so on. So the pattern recognition with colors, at least in some way, it's pretty advanced at the moment. And those black and white people who were doing in the United States analyzing satellite pictures of Soviet Union, they were looking for shapes of the tracks with missiles and so on, because you analyze patterns in principle, yes? But the problem, I think, is other way around, because you have to know how physiology and psychology works, what people are focusing their faces watching art or whatever picture. And as my favorite example is already quite a few years ago on yearly Sony photographic world competition. The first award was given to a photograph of some famous photographer, which was a portrait of two women. After announcing he got the first prize, he announced that this is artificial and computer generated program, which produced a lot of scandals and discussion. Are we going to continue this competition? So,
Yes.
so it seems that at least if you know that you are generating pictures for human perception, there are certain features that humans are focusing on, whether you like it or not.
Oh,
Yes, that's right. And I know it's not, for example, this topological data analysis also apply to recognize the color pictures. Okay, so there's all these complications I mentioned that this is four-dimensional somehow were circumvented, not in satisfactory manner, I would say, but it is obviously the first idea was to use it also this to recognize, to analyze the pictures. Okay.
Okay, Professor Rzążewski?
In all this talk and also in some other remarks, it seems that you've been concentrated all the time at the short distance correlations, yes? Is it certain that the long distance aspect is not relevant for the
No, not at all.
perception?
No. Okay, so I was in my analysis, I was limited to this. What was the result of the experiment? Obviously, I think it was first experiment of this kind which was performed. So definitely there is a place for making many other hypotheses, and then you can have all constants and non-constants as usual.
Bożena, please?
Just a short comment. I'm not sure if it is relevant, but once I read an article about red noise and in particular -1 noise, and the authors also discussed music. They compared several things, and they found that the best music is of Beethoven. It was really at -1 and extending for a very large range of frequencies. So that gave the pleasure.
Yes. So my idea was some time ago to use this also. There is some kind of this kind. So I would advocate this kind of analysis, analyzing music. And I had the idea to apply this to music because you can make some variation of this kind of analysis to analyze time series and to apply to this topological data analysis. I never a chance to implement this idea, but I found that people who are interested in this and who already did something in this, have done something in this direction, but they analyze rather the nature of the sounds, for example, birds. Sounds, okay, and this with this kind of. I dream about doing this for maybe I can also then support the idea that better than us the best. I don't know whether it's true, but I'm close to agree.
If you take into account some measures like power spectrum or something like that, you can prove it. So there's no problem. You can take Fourier transform.
Okay, so this would be one more proof that it is true. Okay.
More
And I
questions?
vote for Bach.
Oscar.
Ja też.
I have a question, like, do you have any idea like how well this like topological fingerprint captures the essence of the artist's style, and do you think it can be used somehow to distinguish between machine-made and human-made?
No, I don't think so. But the idea that because you can always improve the production. If you know the
Of
results,
course.
you can improve the production. I would say that in a sense, more promising is the idea that you can somehow, if you do it very carefully, you can somehow find the characteristic features of a particular paper. especially if he does not change his style as I showed. Okay, but if you look on, I don't know, Matejko's pictures are more or less in the same style, very Malczewski. Okay, so probably you can, but I think I don't see whether this is okay. It could be interesting, but from the practical point of view, it's better to look at the pictures and then you see this common. Great.
Face recognition.
Yes. But yes, okay. I don't believe that you can do it better than you can recognize between fakes and not fakes. Okay, you can always take into account this kind of analysis and produce better.
Okay, now maybe
Mikołaj
we give a chance to online audience. No, then Mikołaj, please.
No questions?
Yeah, just wanted to add a remark because I think from machine learning point of view, it will be interesting to see what will happen if we took like much better models of art and train it on a particular artist itself, like his or her pictures, and see how close those topological diagrams will become. Like,
okay, so you can even apply some known ways of comparing the results. Okay, so I said that we use we have much more results which were not presented here, but you can somehow also find a nice measure of similarity between very complicated patterns. Okay, Wasserstein distance or whatever. Okay, but there are different ways of quantifying it. So, okay, so there is a lot to be done. There are some heavy, behind this are some heavy numerical calculations. So then it always takes time to implement the new ideas.
Okay, so Mikołaj, you wanted? Okay, yeah. One quick question.
So all these pictures, if you look at them carefully, they have a hierarchical structure. There's something, a big large-scale structure, which is composed of smaller ones, not smaller ones. As far as I know, these convolutional neural networks, which are best at recognizing things, exactly can capture that. They sense low-level structures, higher-level structures made of those, and so on and so on. I wonder if this topological way of thinking to some extent captures that, but maybe there's a better way.
So there is the idea of self-similarity, which was also used as one of the measures of complication of the picture. And this here it is more or less explained. Okay, so you divide this in the smaller, so then you can discover whether this is not exactly what you are talking about, because this higher structure could be a different character and there is smaller character, but there were attempts in this direction. Okay, so this is this kind which is called self-similarity. And then you divide this into smaller parts and compare this part with this mother part. Okay, and we did it on our pictures. That didn't differentiate between the two groups. This particular measure didn't do it. Okay.
Okay, thank you very much.